Hi, everybody. I'm excited to introduce Exome today. So, Exome is a new service from True Technologies that is an OLAP data warehouse built specifically for biotech and life sciences applications. So, what that means is it has the set of features that data teams and analysts and scientists and general users of data at companies have come to expect out of OLAP data warehouses, but at the same time has set of specialization and features that make it even more productive when working with bio informatics data and sort of biotech and life science applications writ large. So it really sort of allows folks to take that next step from analyzing data. Maybe they have a bunch of workflows that are, say, doing primary or secondary analysis on the one hand, and then on the other hand, they have a LIMS system, an ELN, et cetera, and they'd like to be able to combine that data and make use of it and then present it in actionable ways to solve whatever business problem is at hand. And Exome, I think, is a really exciting way to do that. So what we're looking at here is a quick example of selecting the type and counting by that type for the output of an RFAM job. So this is actually a GFF file backed on S3, but we're able to add some structure on it and a table and a schema, and then query it directly through our web interface here. So to give a little bit of the lay of land for what Exome is, and of course this is uh, grossly simplified, but we have the web IDE that we already saw. In addition to being in the IDE, there's the ability to connect using Flight SQL to the Exome server, and so this is a pretty exciting, I think, for a number of reasons. One, with Flight SQL and the ability to use that protocol, you can get much higher throughput for data applications than other database connecting methods with Python. So the data comes over the wire faster. In addition to that, the Exome server, by virtue of its domain relevant capabilities, can help uh, reduce the amount of data that needs to be processed in the first place. For example, pushing down region queries on indexed VCF files rather than, say, downloading an entire VCF file and its index, or downloading a set of VCF files and all of their indexes to query a specific region. You can push that region filter upstream to Exome. It can run that and then only return the data that is needed. And then finally, a lot of these domain specific file formats and processing tools are challenging from a DevOps perspective to run, and having a very lightweight ability way in Python without needing a bunch of extra C to, say, parse BAM files or VCF files and use them in meaningful ways is, a big productivity win. And then two of the things that are coming soon that I'm particularly excited about are the ability to connect directly to BI tools. So you can imagine a lot of fun and a lot of useful tools you could build if you could connect superset, say, to your FASTQ data. Maybe you want to maybe you have a sequencing core team in house and you want to be able to build sort of dashboards without a bunch of ETL, say, that have the sequencing quality over time or the amount of bases. maybe you need a vanity number or something. And then, of course, DBT finally, which has become, workhorse of database and sort of data ETL workflows where it's worked and again has become sort of ubiquitous in sort of mainstream business tools, and it gets a lot of play in biotech, but there is a challenge of ETL and data processing, which has had to be done in a very bespoke manner to prepare it for DBT. I think we're at a point where we can sort of offer the DBT use case directly to folks on their domain relevant files. Say a BAM, a BCF, FASTA, FASTQ, GFF, all those fun things. So with that, we'll look at a couple of examples of using Exome. Yeah, so as our first example, we're just going to build off the GFF example from earlier. So yeah, what we can see here again is we can just pretty easily and simply run a query and get the results of that. Um, you might be wondering, okay, type, that makes sense. That of course is a field in a GFF file, but what does the rest of the schema look like? And so we can use the traditional describe keyword here, run a query, and we can see then, yeah, we have sort of the sequence name, the source, the type, the start, the end, the score, the strand, the phase, and then the attributes from the particular GFF file. Um, so this allows us to sort of look and see what might be available. Of course, we could just run a select all from limit 5 to look at this data as well and see sort of yeah, what a sample is. It's obviously always good to look at your files. So um, yes, this is sort of the IDE or the web interface, if you will. We might want to then sort of look a little bit and say, okay, like that is the table that we queried, but as I mentioned earlier, this is backed by some data in S3, and here we can see it is in S3. It exists in this table, and so there is the query engine we just looked at, but then there's a catalog which exists outside of or sort of in addition to the query engine that allows you to have sort of long-term tables and catalogs that can be queried and have information. So yeah, we have table name, catalog name, schema name, that fun stuff. Um, specific file format. This is GFF. A compression type. This is uncompressed. Exon supports sort of uncompressed gzip, bgzip for the relevant file types, and NZ standard. There are no table partitions here, so Exon supports a number of specific uh, 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 filter pushdowns for index file types. But in addition to that, on sort of all file types, it supports Hive-based partitioning. So, say for example, rather than this sample here, we could put sample ID equals this, and then if we were to have that in our file structure, we would get that in our schema, which can be nice to sort of augment the underlying files with say sample metadata or other metadata. But in addition to that, you then can have those filters be pushed down, so to speak, and any file that doesn't match that filter is pruned, so to speak, and thus you reduce the amount of data that needs to be processed, thus increasing the query time. So this is a specific file. We can sort of go back at the top and look at, say, our catalog, our schema, particular schemas, and then these are our tables. And so this is a metagenomic sample that has prodigal output, PFAM output, the actual proteins, contigs, and so forth. So this is just a sort of high-level example of yeah, the catalog, and yeah, we ran a query as well. All right, so as the second example, I wanted to show a script, Python script that is used to connect to the Exome service. So we have this Exome library. Really, it's a kind of a thin wrapper around the Flight SQL Python library, and the only things it does in addition to it are support the authentication handshake here and the health check here. And so what this script does is does a quick check of the health of the service to make sure it's up before we try to authenticate. We use the same email and password that we used for the web service. And then we have a simple query here that is selecting all from this FASTA table. And this FASTA table is actually backed by a FASTA file of amino acids. So it's 500 rows. It's not like large bro count, but there's just a lot of strings at the end of the day. And so um, yeah, so we can see here we have this sort of standard context manager based on connection handling. So we create a connection, generate a cursor from that connection, run the query against it, fetch all the results in arrow format, convert that arrow format to pandas data frame, and then print. And then, so full disclosure, there is a error when things are coming out of the context manager, and so we can see that we should be able to connect to the service and then get the results again of a fair amount of amino acids. But we will sort of have this abort error at the end. So what you can see here, though, is just a pandas data frame with the ID, the description, and the sequence. Basically, exactly what you would expect, mapping a FASTA file onto a tabular format. So I wanted to show one final example, which is what it looks like to query a VCF variant data set through the web interface, which can be also queried through through other methods. So what we have in front of us are a set of VCF files. So this phase one analysis results, which is from the Thousand Genomes Project. Each sort of organizational pair, if you will, has a VCF file, which is the actual variants, and then the TBI file, which is the index, which associates locations in the genome with byte offsets in the VCF file so that we can query faster if we only need a specific region. If you want to go to our blog, you can see sort of the technical details of how we make use of the VCF files and the VCF indexes in the querying. So um, yeah, what we have here are a number of data sets. There's about 120 gigs in total. And so I'm just going to delete this section, but I just wanted to show you uh, the back end, if you will. So yeah, we're going to do a select all from that Thousand Genomes Analysis Phase 1 project. We're going to use this VCF filter, which is a special UDF that takes a region, a chromosome, and a position and evaluates to true where the chromosome and the position match that particular um, region filter. And so, like for example, we only wanted Chrome 17. I can just put that in here and run the query, and then and then get the results. Um, like you might imagine, the other chromosomes which are available can also be queried, like chromosome 17 or whatever it may be. Yeah. So with that, I will leave you there. Thank you.